Now, in the previous video, we discussed independent events and the multiplication rule that applies to those independent events. We discussed why one event didn't necessarily affect the likelihood of the next event occurring. However, when two events are dependent, in other words, the probability of the second event depends on what happened in the first event, then we simply just can't multiply those two events together. We have to use a little adaptation to the probability rule. This states that the probability of the two events occurring says that the probability of E and event occurring is the probability that E will occur times the probability F will occur, given that you know E has already occurred. So it's that we know this piece of information in order to determine what the probability of F will be. Also note that in a small random sample that they're taken from large populations without replacement, it is reasonable to assume that they are independent. Just like in the previous video when we talked about left-handed people. We knew that there was a 13% chance of selecting a left-handed people in a population of 330 million U.S. citizens. Clearly, when I take that left-handed person out of the pool, I'm still left with 13% left-handed, even though I have one less left-handed person in the hat. But that's because there are so many people, 330 million people as a population. Taking one person isn't really going to change that 13% very much to make a difference. So when you're taking a random sample out of a really large population, we assume that there's just independence anyways. As a rule of thumb, if the sample size is less than 5% of the population, we treat them as being independent. Examples. Let's suppose a single card is selected from a 52 card deck. What is the probability that that card is a club? So again, we've got our cards in front of us, which I'll show you here. And I want to know the probability that you're going to select one club out of all of these cards. Well, I know the probability of selecting a club is going to be 13 out of 52, which is 1/4 of the deck, which is 25%, right? Because there's 13 cards. However, now let's suppose a single card is drawn from the deck. We're told that the card is black. What then is the probability it's a club? So I'm looking at all of these cards and I'm told that the card is black. So that means if I know that the card is black, that means it either has to be a club or I know that the card has to be a spade because you're told it is basically not red. So if you're told that the card is black, I'm specifically looking for the probability of selecting that club just like the last example, but this time I'm given the extra piece of information that I know that it's black. So we're looking for the probability of selecting a club given you know it's black. So no longer am I dealing with a whole deck. This time I'm only dealing with the cards that I know about the characteristic in that it's black. So now I know I'm only dealing with 26 cards since I know the card's black. Out of those 26 black cards, what's the probability I'll select a club? Well, there are 13 clubs out of all the black cards, which is 50%. So the point is, when you know something about this particular person or object, you're eliminating some of the objects that are in your total sample space. For example, if I have a hat of a whole bunch of names, let's say 100 names, and I know the person has blue eyes, well, I'm going to get rid of all of the names in the hat of people that don't have blue eyes, and I'm going to focus on just those that have blue eyes, kind of like a detective. You whittle away at the characteristics, what you know, and you only look at those that have those characteristics because you're going to eliminate all of the others that don't. So in part C, given that you know it is a face card, what is the probability as a queen? So we're looking for the probability that it might be a queen given we know it's a face card. So we always put what we know in the second spot. So we know it's a face card. So out of all of the cards that I had before, how many are face cards? Well, I know that there are 12 face cards in the deck. There's a Jack, Queen, King of 4 different suits. Out of all of those face cards, how many are queens? Well, there are 4 queens out of all 12 face cards. And if you need some help, you could always go back to that previous page where we put all of these on the previous videos. And these are all of the face cards over here. There's 12 of them. And you're going to see that there are 4 face cards out of all 12. Or excuse me, there are 4 queens out of all 12 face cards. So always refer back to this picture if you need to. So there are 4 queens out of 12 face cards, and that obviously comes out to 33.3%. What is the probability that I will draw 2 cards without replacement and they are both queens? Okay, so I'm going to go to my deck of cards. Okay, I have my deck of cards here, and I'm going to randomly select 2 cards without replacement. So I'm going to select one, and then I'm not going to replace it. I'm going to hold it in my hand, go back into the deck, and select the second card. So 2 events. I want to select the probability of getting a queen. Then I want to select the probability that I'll get a queen given I know I already selected a queen. So this is going to be the probability of selecting the first queen. Well, there are 4 out of 52. Well, now if I have that queen, let's say I took this queen and I take it out of the deck and I pull it aside, and I'm not going to replace it. I now have only 51 cards left in the deck, and I now have only 3 queens left in the deck. So the probability I select the first queen, whether or not I selected that queen, is going to affect the probability of whether or not I'll select the second queen, since that probability changes. And it's all because I didn't replace the card back into the deck. So when I multiply those two together, I get 0.005, or less than 8%. And this is obviously very different than question 4 from the previous page. So on the previous page, when we were talking about selecting a possibility of 2 queens, it was this question here. A single card is randomly selected from the deck of cards and then put back in the deck. What's the probability I'll select both queens? Well, that's because I replaced it. I replaced that card back into the deck. Okay? Because you put the card back into the deck, you're now back at 52 cards and you're back at 4 queens. So this is not what we call conditional probability. These are totally independent events. It doesn't matter what I do because I still have the same likelihood the next time. In this example that we just did, these are considered dependent events because I am not replacing the card, so I have less cards to deal with the next time, and I might have less queens as well. Okay, so no replacement when we're dealing with cards means dependent events. Some might call this conditional probability. In other words, it's conditional. The probability is conditional depending upon what happens first. So let's look at some examples. The following data represents the number of traffic fatalities in the United States in 2009 by seat location and also by gender. So again, we have males and females, but we also have whether they were driving the vehicle or whether they were a passenger in the vehicle. Okay? And there were 57,000 deaths by traffic fatalities in the United States back in 2009. So it says, among the female fatalities, what is the probability that a randomly selected fatality is a driver? Okay, so among the female fatalities, so it means I'm given the fact that they're female. So I'm looking for the probability given that they're female. So I know that they're female. It's asking me to find what is the probability it being the driver. So I'm looking for the probability that the person is a driver given that they're female. So if I know that they're female, I'm only going to look out of the female fatalities. My denominator will now only be out of the females since I'm ruling out all of the males. So the 18,219 becomes my denominator. And out of all of these female fatalities, what's the probability she is a driver? 11,000. So that's a 65.1%. Among the passenger fatalities. So this time I know the person is a passenger, and that's what's given. What is the probability that the person is female? So I'm looking for what's the probability of selecting a female given you know that they are a passenger. Well, I know that there were 12,000 passengers that were killed in traffic fatalities. And out of those 12,000 passenger fatalities, how many of these 12,000 were female? 6,300, which comes out to 49.6%. Suppose you are a police officer and you're called to the scene of a traffic accident with a fatality. The dispatcher states that the victim was driving, but the gender is not known. What is the victim? Is the victim more likely to be male or female, and why? Well, let's do two separate calculations. Let's do male, and then we'll also do the female. So in order to determine whether the victim is likely to be male, we are called to the scene of the accident with a fatality, and the dispatcher states that the victim was driving. So we know that the probability of this person, we know the person is driving. We're looking for the probability that they are male, given you know that they were driving. So we're only looking out of the total of 44,000 drivers. There were 32,873 fatalities that were male when we knew that they were driving. So this comes out to 73.5%. So we're going to do the same thing for female. So I'd like you to calculate what that would be. Maybe pause the video and then come back and check. So we're looking for the probability of selecting a female given you know that they were driving. Out of the 44,000 fatalities of victims that were driving, we know that there were 11,856 female drivers, which is 26.5%. So to answer this question, is the victim more likely to be male or female? The answer would be male. According to the U.S. Census Bureau, U.S. Bureau of Labor Statistics, there is a 4.9% probability that a randomly selected employed individual has more than one job, or in other words, a multiple job holder. Also, there is a 46.6% probability that a randomly selected employed individual is male, given that he has more than one job. Okay, so we know a lot of information up here. So what do we know? We know the probability of being a multiple job holder, and that was given right here. This is the probability of being a multi-job holder. We also know this probability. This probability is the probability that that a randomly selected employed individual is male, given they have more than one job. So this is the probability of being male, given they're a multi-job holder. So I have the probability of being a multi-job holder, but I also have the probability that somebody might be male, given you know they're a multi-job holder. So the question is asking us, what is the probability that a randomly selected employed individual is a multiple job holder and male at the same time? Well, all we have to do is multiply the probability of somebody being male times the probability of them being a multiple job holder got that backwards. The probability of them being a multiple job holder times the probability that they will be male, given you know they're a multiple job holder. And I have all of this information up here in the problem. Okay? The probability of somebody being a multiple job holder is 4.9%. So this is going to be 0.049. We're going to multiply that by the probability of somebody being male, given you know they're a multiple job holder, which is 46.6%. And that's going to come out to a total of 0.023, or 2.3%. So would it be unusual to randomly select this employed individual who is a multiple job holder and male at the same time? Is that number unusual? And the answer would be yes. 2.3% is unusual since it's less than 5%. In section 5.5, we're going to discuss the last of the probability, which is counting techniques. Counting techniques are a way of counting the number of ways that something might occur. And there are 4 different techniques that we are going to cover. The first one is the multiplication rule of counting, which is the most elementary way of counting. Very simple to use. So if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the next choice, and so on, we simply just have to multiply all of those choices together. An example of this would be if you go to a fast food restaurant and you have a choice of selecting a sandwich, a side item, and a drink. Well, how many different ways can you order a meal? You would multiply the number of ways of selecting a sandwich. Let's say there's 12 sandwiches on the menu, times the number of ways you can select a side item. Let's say there's 3 side items you can pick from, times the number of drink options. Let's say there are 6 drink options. So when we multiply 12 times 3 times 6, we're going to get the total number of ways you can order a meal differently every single time. A lot of people like to think of this as a tree diagram. So for example, again, you go into the fast food restaurant and you first have to order a sandwich. And you know that there are 12 different ways in which you can order a sandwich. So you can order any of these 12 sandwiches. Okay? After you order the sandwich, you now have to order a side item. Well, if I've ordered, let's say, the Whopper, I now have to order one of 3 different sides. If I order, for example, the chicken sandwich, I still have to order one of those 3 particular sides, and so on and so forth. Then I have to order the drink. There are 6 possible drinks, so if I order this particular side item, I now have to order one of 6 drinks. So you can see how the number of possible options is going to get quite large, quite fast. So rather than draw this tree diagram every single time, it's much easier to just multiply each of those options together. We also need to discuss what's called the factorial symbol. A factorial symbol simply just means multiply each number by every integer underneath it. So for example, 4 factorial is equivalent to 4 times every integer underneath until I get to 1. This is simply equal to 24. It's pretty easy when the numbers are small. But what if the numbers are big? Well, our calculators can help us with that. Okay, using my favorite calculator, the TI-30X, we have the factorial symbol. So if I did 4 factorial, the factorial symbol is going to be located here under the probability button. A lot of the things we do will be in the probability button here. And you'll see the third one over, I have to right arrow over to the factorial symbol, and you'll see you'll get 24. If I tried 10 factorial, you'll see that these numbers get quite big quite fast. So obviously 100 factorial is going to be even larger. In fact, it gives me an overflow because it is so big. Okay, the 4 types of counting techniques are using what's called combinations, and then we have permutation. So there's only one type of combination, but there are 3 types of permutations. The combination, the most important thing about combination is that the order does not matter, okay? The order in which an object is selected does not matter. So in other words, AB is the same as BA. An example of this would be a lottery ticket. So if you go and purchase a lottery ticket, a general lottery ticket, not with the Powerball or anything like that, the order in which you select the numbers doesn't matter. So for example, if I have a lottery ticket with the numbers 1, 16, 24, and 36, but on television, when she's pulling those ping pong balls out of the machine, let's say they come up as 36, 16, 24, and 1, I have still 1. So the order does not matter for the lottery. So this would be an example of a combination when the order in which you select the items does not matter. It's just the grouping of all of these items is equivalent to this group. All of the items are the same inside the group. Now these 3 items for permutations, order does matter. So when order in selected actually does matter. So AB is not the same as BA. An example of a permutation would be, when order does matter, would be an example of a garage code to get into your house. If my garage code is 1, 2, 3, 4, but I entered 4, 3, 2, 1, I will not be let into my home because that code is not the same. So order definitely does matter. Now, why are there 3 different types of permutations? One is a permutation of distinct items with replacement. A good example of this was selecting 2 queens from a deck. Okay, I'm going to select 2 queens from a deck, but I'm going to replace the card each time I select a new card, so therefore it's not conditional. They're independent events. Then we have permutation without replacement. So an example of this would be a deck with non-replacement. These would be considered dependent events. Then the last one is a permutation of non-distinct items. So for example, if I asked you to line up, I have 4 beer glasses that are heirlooms, and I wanted to line them up on my bar, right? And these are my 4 beer glasses, and they mean a lot to me, so I want to display them. And I asked you to rearrange these, and how many ways you could rearrange these on your bar. Well, if you look at these first 2, they are both red, and they both look identical. So in other words, if I were to rearrange just these first 2 glasses, would it actually be a different permutation? Would it actually look like a different arrangement? And the answer would be no, because these 2 items are non-distinct. They look identical. So even if I swap the order of these first 2 items, it's not going to appear that anything has changed. So when all of your items aren't exactly unique, then you have this non-distinct item option. So we're going to go through all of these different scenarios on the next page. But first, what I'd like to show you is a flow chart on what to do when. So for example, ask yourself, the first thing, when you're asked a question, ask yourself if order matters. If order does not matter, you automatically have a combination. And that's the easiest one to find because it's the only one that you will ever have to use. So here's an example of how to use the combination formula. How many ways can you select 5 people from a group of 20 to be part of a committee? So I've got 20 people in a room and I'm randomly going to select 5 people out of that room. Or picture 20 names in a hat. And I'm going to select 5 names out of the hat. And those 5 names are going to be part of a committee to help me with something. Does the order matter in which those 5 names are selected? And the answer is no, because all 5 are just part of this committee. The first person doesn't hold any special power versus the 5th person that's been selected. They're all equal. Since order does not matter, we're going to use this formula. We need to determine what N and R are, what those values are. N is the value of the total number of names in the hat. In this case, I have 20 names in the hat. So 20 in this case is going to be the N. R is how many names I'm going to draw out of the hat. I'm going to only pick 5 names out of the hat. Could those numbers match? Surely. I could pick all 20, but usually the R is less than the total. So we're going to use 5 for the R's. So when I plug the 20 and the 5 in for N and R, you're going to get this formula right here. So 20 factorial divided by 5 factorial times parentheses of 20 minus 5 factorial. So let's go ahead and do 1 in our calculator. Okay. So in my calculator here, I'm going to do the numerator, which is 20 factorial, and I like parentheses, so I'm going to use them. Some calculators are not necessary, but I'm a fan. Divided by the denominator, again, I like parentheses, so I'm going to do 5 factorial times 20 minus 5 factorial equals. Oh, and I got an error, so I did something wrong. What did I do? So the calculator, some of the numbers were too big for the calculator to handle. So what I did to try to fix this is I made the calculator, instead of doing down here 20 minus 5, I did 15 factorial instead. There was something in the internal calculation that it was overflowing the calculator. So again, I forced the denominator to just be 5 factorial times 15 factorial, which is the same thing as this. And when I do that, I get the right answer, which was 15,504 ways. Now, there's a shortcut to this. We could simply just type this into our calculator. 20 combination 5. So if I do 20 and then you go back up to your PRB tab, you'll notice you have the combination right here. And if I do 20 combination 5 items taken out of the 20, you're going to get the same answer, which is a heck of a lot easier than doing it using the formula way. Of course, on the exam, either way is acceptable. You don't have to remember this formula if you can just use the combination in your calculator. So if you don't have the combination in your calculator, I would definitely suggest you get that option. It will make your job easier on exam day. Now let's look over here at the permutations. Okay, so let's say order does matter. The next question you have to ask yourself is, are all of the items being lined up, are they all different from each other? In other words, are they all unique? If the answer is no, we have some items that are not unique. Okay? If the answer is no, we have a permutation with non-distinct items without replacement. An example of that would be, how many ways can I rearrange the letters in the word Indiana? And you'll notice that some of these letters are not unique. If I were to rearrange this I with this I, and I swap the location of that I with the other I, the word doesn't look like it appears to have been changed. Since those letters are not all distinct or unique, we have this scenario here, this formula. To utilize that formula, the n on top is the total number of letters. In this case, there are 7 of them. But then we have to divide out by the number of non-distinct items. Since there is more than one I, there are 2 of them, I divide by the number of i's in the total of n. There are 2 i's. Then I divide by the next non-distinct item. Well, there's also 2 n's. So I divide by 2 n's. There's only 1 d, so I can have a 1 down there. Putting in that 1 is not going to change the value because dividing by 1 doesn't do anything, but I like to still show it. I also have 2 a's in there. And you'll notice that all of these numbers then should add up to the total on top. That way I know I counted all of them. So if I put this into my calculator, I would use the factorial symbol. So up top I have 7 factorial divided by 2 factorial, 2 factorial, 1 factorial, 2 factorial, and I should get 630 total ways. So there are 630 ways I could rearrange these letters, knowing that you can't just mix and match the i's because that's not going to create a new permutation. Okay, so now back to the top. What if we said order does matter? Now we decided all of the items are actually unique and they're all different from each other. Now you ask yourself, can an item either be repeated or replaced? In other words, can I repeat the same item twice? Or can the same name be picked 2 times in a row? Or the same card or the same digit be used? If it is yes, you can replace that item. This is no different than selecting 2 queens out of the deck because they're not they're independent or not dependent on each other. This is independent events versus dependent events. All we have to simply do is multiply all the possible ways together using the multiplication principle that we learned on the previous page. For example, how many ways can you enter a 4-digit lock number until you get it right? Like a briefcase, right? Let's say there's the spinning code of 4 digits on a briefcase and you need to open it up. Well, you've first got to get the first digit correct, and there are 10 possible ways you can get that first digit correct. The numbers 0 through 9, those are 10 possible digits. You can repeat the same number again. In other words, if I selected 1 for the first digit, I can use 1 again for the next digit. So replacement or repetition is allowed. So I still have 10 possible codes I can pick for the next one, and for the third code, and for the 4th digit. So this is 10 to the 4th power, which is 10,000 different ways. Now for the permutation of distinct items without replacement, this time we're not going to replace the item, like selecting 2 queens, for example, but I'm going to keep the first queen out and not replace it back in the deck the second time. This means it's not replacement or they're dependent events. We recommend you use what's called the permutation formula. It looks very similar to the combination formula that we used up here. It's just a little bit different. So, for example, let's say I have a group of 20 people in a room and I want to select a president, vice president, secretary, and treasurer. So I'm basically selecting 4 people out of 20. Similar to the committee that I was selecting up here when I was doing the combination. However, this time I'm calling this one a permutation. I'm saying order matters. And the reason order matters in this particular group is because I'm specifically selecting a president, vice president, secretary, and treasurer, and they have specific roles in which they need to serve. So the first person selected will be a president. The second person selected will be a vice president, and so on. So because the order matters in which they're selected, this is going to be a permutation instead of a combination. The order matters, so if I put in my calculator 20 factorial times 20 minus 4 factorial, I'm going to get Well, 20 minus 4 is 16, so let me just do a shortcut and just do 16 factorial down there. And you're going to get a total of 116,000 different ways I can select those 4 people. Now, of course, the shortcut would be just to do the NPR in our calculator. So 20 NPR 4 should give us the same value. And this obviously is going to be an easier way to come up with the same value. So let's go through a couple of scenarios using these, and then we'll wrap this chapter up. So for number 1, outside a home, there's a keypad that will open the garage if the correct 4-digit code is entered. So this is very similar to the locked briefcase example that we just did. And it asks how many codes are possible. Okay, so I'm going to go up to that keypad. I'm going to punch in the first digit. And there are 10 possible ways I can select that first digit. Using the multiplication principle, I know that there are 10 different ways of selecting each of the correct codes or each of the correct digits for the complete code. This is the multiplication principle because this is a permutation of distinct items with replacement, because you can utilize the same code or the same digit can be utilized multiple times. So you're replacing that number and you're going to use that same number again possibly. All of the codes are possibly distinct. Okay, so this is obviously going to come out to 10,000 possible ways, or 10 to the 4th. So there are 10,000 different 4-digit codes. Now, there are 3 students from Part B. So what is the probability? Now it's asking for the probability. So what is the probability of entering the correct code on the first try, assuming the owner doesn't remember the code? Okay, so it's not asking for how many ways the codes could be correct. It's saying what's the probability that I'll get this right on the first try. Probability is always a division. So the probability is going to be 1 in 10,000. So it's a very, very, very small probability. In fact, it's less. It's 0.01%. So the first question, be very careful. If it says how many codes are possible or how many ways can something happen, you're looking for a big whole number. If I'm asking for the probability, make sure you give me a number. Always recall the probability has to be a number between 0 to 1. So if you answered this down here, that would be absurd because probability has to be a number between 0 to 1. How about if 3 students from a 20-person classroom are to be selected randomly to do 3 questions on the board of various difficulty levels? How many different presentations are possible? So, does the order matter? And the answer is yes. Order does matter because the different presentations, 3 questions on the board. So the 3 questions, the order matters in which those three people are selected because they're going to get 3 different questions. So the first person might get an easy question and the second person might get a hard question. So since each question is a different difficulty level, they're not all the same question, each person getting a different one is a different permutation. So this is going to be a permutation of 20 total items, and we're only going to select 3 people from the probability of 20. So we're doing a 20 permutation of 4 items at a time. 3 items at a time, excuse me. So we're going to do 20 permutation of 3 students to select 3 different questions, and we're going to get a possible of 6,840 different ways that those 3 students can be selected from that group of 20. How many different ways can you organize the letters in Mississippi? Well, this is a permutation because we're organizing the letters, so order matters. Clearly, if I mix the M with the P, then that's a different permutation. Order matters because then that word would not spell Mississippi anymore. Also, these are not distinct items because you're going to notice some of these letters are occurring more than one time. So this is a permutation of non-distinct items without replacement because I'm not going to use the same letter twice. So we're going to do the total number of letters, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total letters in the word. Then we have to divide by the number of times each letter occurs, or the number of items that repeat. So there's only one M. There are 1, 2, 3, 4 I's. There is 1, 2, 3, 4 S's and 2 P's. And you'll notice that all of these numbers will add up to 11, so that way I know I hit all of the letters and accounted for all of them. So if I put this into my calculator, I have 11 factorial, and I'm going to divide that by 1 factorial, which I don't really need to do because that doesn't change the value. And I get a total of 34,650 different ways of spelling the word Mississippi, or rearranging those letters. So now let's suppose that there are 55 Democrats and 45 Republicans in the U.S. Senate. A committee of 7 senators is to be formed by selecting members of the Senate randomly. So what is the probability that the committee is composed of all Democrats? So note that I'm asking for probability, not the total number of counting ways. I'm looking for the probability. So I am going to be dividing. I like to look at the denominator first. I'm looking for the total sample space in the denominator. There are 100 total names in the hat. And I want to pick a total of 7 senators. Is this going to be a combination or a permutation? Well, since I'm just selecting senators to form a committee, this is going to be a combination because order does not matter. Now, in the numerator, I specifically want all Democrats. So I want to select 7 from the group of all Democrats. I want to make sure I absolutely get Democrats. So I'm going to select 7 out of the group of 55. So if I select 55 total Democrats, oops, and I only want 7 of them, and then I have to divide that by, I might put that in parentheses. You're going to get a probability of 0.0127. So that's less than 5%. This would be considered unusual, right? It would be unusual to go into this hat of 100 and select all 7 Democrats. But I kind of figured that that would be unusual to select all 7 of one type. So now what's the probability the committee is composed of 3 Democrats and 4 Republicans? There's that word and. And means multiply. So when we're finding probability, we're still selecting 7 out of 100, so the sample space has not changed. But up top, we want to multiply together the likelihood that we will select first 3 Democrats, and then we go back into the hat, and now we're going to select 4 Republicans. So when I put all this into my calculator, you're going to get a 24% chance. I would advise probably putting those into parentheses if you're going to use your calculator. Last question. Suppose that you have just received a shipment of 100 televisions. Although you don't know this, 6 are actually defective. So sometimes I like to look at a picture. If your reading comprehension is not great like mine, and you have 100 televisions, 6 are defective, and the rest are non-defects. So I'm clearly not going to do this 100 times. but that's what your shipment's going to look like, okay? To determine whether you'll accept the shipment, you're going to randomly go in here and you're going to select 5 of these random TVs and you're going to test them all. And if all 5 of them work, then you accept the shipment. So if I select, for example, these 5 TVs right here, I'm going to accept the shipment because I randomly selected 5 non-defect TVs, so I assume that they're all good. However, if I selected at least just one of these, then I'm not going to select the shipment because I've selected a defect. Okay? So the question is, what is the probability that I'll accept the shipment? And the only way I'll accept the shipment is if all of them work. So in the denominator, it's a combination. I don't really care about the order in which I test the TVs. Regardless if the first one's the defect or the last one's the defect, I'm still going to reject the shipment. So the order in which I test the TVs does not matter. So it's a combination, and I am going to select 5 out of the shipment of 100. Now up top, I want to make sure that I accept the shipment. So I'm going to select 5 out of just the televisions that are non-defects. And if I counted all of these, there will be 94 non-defects, because remember 6 are defects, so that means the other 94 must be non-defects. And this is going to give me a 72.9% chance of accepting a shipment.